the story of Sergio. He graduated from Technion right here in telecommunications engineering.
Yeah.
All right. Yeah. And after that, he moved to the United States to do his PhD in Colorado State University first, and then MIT. All right. And nowadays, Sergio is an assistant professor at UCLA, and he also has an appointment at SLAC at Stanford University. And Sergio works on, as he says, transformational photon and particle sources. So very cool lasers and particle accelerators and stuff like that. And he applies these developments in basic environmental sciences, medicine, and industry, and a couple more things that I think you will talk about today, right? So without any further ado, so Sergio, I think the best thing is for you to introduce yourself and introduce your research.
Yeah, thank you so much. Yeah, appreciate it. Yeah, thanks for the introduction. You covered most of my affiliations. I will be covering basically some of the things that he mentioned, how we develop very unique instruments and try to run some biology or chemistry and understand them at the molecular level. But before I go into that, I want to share that I'm extremely happy to be here. This is my homeland. I grew up in Hernani. So I really appreciate Aitzol's invitation to give a talk, and Teresa right here was also instrumental in making that connection. So thank you both very much. I also wanted to make a proposition, since it's a relatively quaint meeting. Please feel free to interrupt anytime and ask any questions. We can clarify a little bit and then have more of an open discussion at the end. Okay, but yeah, I'd rather make this more of a discussion than a spiel. But what I'll do today is kind of talk about how non-equilibrium dynamics of water, and I'll explain in a minute what that is, can be a playground for a huge ensemble of chemical and biological processes. Okay, that will cover essentially all the key instrumentation, methodology, science, and a lot of engineering behind making these experiments happen. But before I do so, what are non-equilibrium physics? This is a very broad sort of term. Non-equilibrium physics means anything that is not in thermodynamic equilibrium, and it really runs the gamut from anywhere in the astrophysics domain to plasma physics to living organisms and even quantum systems. So non-equilibrium systems are abound. They're very elusive, but they're constantly surrounding us and sort of interacting with their environment. But today, let's focus on just water, non-equilibrium systems and water. For that, this is a bit of an outline. My presentation is going to be sort of focused first on what we call ultrafast molecular dynamics. So what happens to molecule under certain excitation, what happens not to it in isolation, but through collective systems or many body interactions, right? Particularly those that escape or evade thermalization, or what happens before something becomes thermalized. Now, we need to observe these dynamics, and in order to do that, we tend to probe them. And what we do is, as Aitzol mentioned, really sophisticated electron and X-ray sources. So this is how we probe the state of them. And the third element is how we can actually orchestrate these dynamics. While they're elusive, one has to trigger them or excite them. Eventually, if you understand them more, you can control them. And so we also develop photon and electronic wave packets to control them. So basically, you have a molecular system, you try to control it, or get started with some photon wave packet, and then you probe it with an X-ray or electron beam in the ultrafast range. Yeah? Before we go into that, why is any of this important? I kind of drink my own Kool-Aid. I mean, I believe my own spiel, but maybe we should always repeat that the idea behind understanding ultrafast dynamics is that the electronic motion, for example, in an atom or a molecule, that tends to happen in the attosecond time scales right here, can then yield some larger atomic motion or molecular motion, for example, isomerization or dissociation, that goes into the femtosecond and picosecond time range. And then you kind of naturally begin to grow in scale and in time scales, and you go from atomic molecular ensembles to maybe living organisms, cellular activity, and then even electromechanical, biological processes that happen in the macro scale. So what we try to do is understand how the early dynamics of any photoexcitation can yield any functional properties in any material. And that's commonly shown graph. It's sort of shows you the entanglement between the ultra small and the ultra fast. Naturally, things that are really small in the angstrom or nanometer range, which are single atoms or molecules, have associated timescales in the femtosecond range. This is 10 to the minus 15 seconds. Some of you might be familiar with it, but it's extremely fast. And how you can begin to build these systems collectively to provide functional organisms, for example, viruses, or even electronic sort of systems, and those go associated with picosecond, nanosecond, timescales, and so on. A good example is, for example, radio frequencies, or 5G in your cell phone goes associated with microscale level chips and photonics. So when it comes down to the ultrafast, now the question is, how do you measure these things? To give you an idea, most of the electronic excitation happens in the attosecond range, and it's hard to grapple how much an attosecond is. I like to usually say that an attosecond is to 1 second, as 1 second is to the entire lifespan of the universe. So this is an extremely fast time scale. So capturing those motions is not very straightforward, and we definitely don't have cameras that can take that speed. So this is the basis of how we run these experiments. So let's say this is our molecular system, and we sort of trigger the motion of that system with these green lasers here. That would be what I called earlier the drive or the pump, whatever you use to orchestrate it. And then I'll run it again. And then the red shot is something that comes sometime later. In this case, is X-rays or electrons, and you capture a snapshot. Every time you take a snapshot, you destroy the sample. So you got to repeat it multiple times. But if I can control the timing between the green pulse, that is when the dynamics start, and the red pulse, when I probe the dynamics, I can take a lot of frames. Right now, with the current technology, we can take 4 or 5 frames in different time scales. Eventually, we might be able to make molecular movies, but it's quite literally stroboscopic imaging. This is all thanks to these very sophisticated techniques and instruments, and the advent of these different technologies have really, brought many breakthroughs in life and energy sciences. One of them, for example, is we have a much clearer understanding of the photosynthetic cycle of Ps2. Ps2 is this macromolecule for system 2 that is in charge of sort of staying idle, waiting for one photon from the sun, undergoing some conformational change. This will be this one photon. After some time, a few nanoseconds later, it absorbs another photon and undergoes multiple structural changes until it goes back to the original state. And in that process, it releases some charge. And this is what we understand to be the first and foremost process in photosynthesis. And this was just uniquely available to us as a process that was confirmed just a couple of years ago. Another idea that is quite revolutionary is that we can quite literally visualize chemical reactions as they happen atomically and molecularly. So you can see here, in this case, we have NMN, and these are different snapshots that are recreated from these scattering signals of these X-ray images that we've taken, where we can see molecular rearrangement. In some cases, you can see the dissociation pathway. So we can see molecular reactions again, either photoreactions or chemical mixing reactions live, and potentially understand them. And this has vast implications in chemical engineering. But today, according to the title, we're going to delve a little more deeper into the biology. And it so happens to be that most of the biology that we study is light triggered. It's not a coincidence that I showed you here for system 2 that reacts to light. We study a lot of rhodopsins. These are the proteins in our eyes that are in charge of enabling us to see color, for example. But when you can trigger these, when you cannot trigger these systems with light, it becomes a bit of a problem in how you can observe this molecular dynamics. So this is a bit the topic that I'll be talking about today. And by this, I mean, let's just take water as a sort of generalized medium that we can use to exploit a vast ensemble of dynamics, and not just those that are photoactivated. So one of the things that I want to sort of break apart here is, water is oftentimes considered as a passive medium, but in reality, it's really reactive, and it's really much what drives a lot of the chemistry and biology and physical chemistry. And much of it has to do with the hydrogen bond network. You might be familiar with it, but this is essentially the loose network that's created between different monomers that's in charge, for example, of giving you the crystalline structure when you create ice water, right? But it's disorder in liquid water. And, spoiler alert, I'm going to be talking about terahertz as a way to control the librations of water. And the vibrational motion is essentially, you can see here a monomer, right? H2O is this type of vibration. There's many other kinds of vibrations, but these can be excited in the terahertz range. And here I'm using terahertz in really loose ways. So terahertz anywhere from we like to think in microns, is anywhere from 5 to 6 microns to the millimeter range. And frequency is a couple terahertz to a fraction of a terahertz, or 0.1 terahertz or so. So people tend to, yes.
May I interrupt?
Yeah, please.
Just a question. What is exactly a libration? What's the difference between a libration and a bending mode?
Yeah, so I'll show in a little bit the diagram, but basically bending modes are higher order. So if you have the monomer, a bending mode might be OH. It's kind of vibrating like this. This is more, the entire monomer aligns with electric field, but it's just moving as a whole fabric. So it's a more baseline, more foundational vibration, yeah. And it's because the field is lower, yeah. I'll cover a little bit that in more detail, thanks. So let's see, let's talk about some potential applications in a really graphic way. Imagine that you have water. Here is a cluster of water. I shoot it to its poles. And this is what I mean by non-equilibrium, right? You're going to have some absorption the same way that you can heat up things on your microwave, right? You have microwave absorption and things get heated, right? But there's, in the ultrafast domain, temperature doesn't really make sense until there's a thermalization process. So what happens? In the femtosecond to picosecond range, you are going to move all these monomers and you're going to disrupt your hydrogen bond network. And then in the nanosecond and later, you finally have some thermalization, some equilibrium state, and now I can perhaps say, okay, I had this much temperature. But it's this pathway from non-equilibrium to equilibrium that can make a huge difference. And so that's a lot of what we'll talk about today. And so this is broadly speaking what I'll delve in a little bit later on, the power of controlling the hydrogen bond network with terahertz. One, for example, in biochem and biology, we can have, for example, enzyme and protein activity. What you're seeing here is a big protein lysozyme surrounded by a lot of water. These are the red dots. If I shoot a terahertz pulse here, I might begin to control the vibrational motion of water. And this can catalytically increase or decrease some properties of this protein, for example, binding to a drug or an inhibitor. So I'll delve into that example. This is the primary example for today. The other two that I won't have time to touch on is I could, for example, reduce hazardous waste into non-hazardous waste with water. If I put enough energy into water with the terahertz pulse, I can create a equivalent temperature. Again, we can't define the temperature, but I can deposit enough energy that it can be supercritical-like. So supercritical water is often used to reduce hazardous waste because it has full miscibility, meaning it becomes a super solvent. And it can be done with relatively low energy because at these time scales, I deposited all the energy into the water, but water doesn't have time to evaporate quite yet. Remember, in my world, a nanosecond is a lifetime, right? So for picoseconds, my water is in liquid water density, but it has supercritical-like water temperature, right? So it can become a super solvent. And last but not least, I can actually control water, not only to create supercritical-like water, but control its phase state with this temperature/stress or pressure diagram and access other parts of the phase diagram of water that are relatively unknown and accessible. And for example, study atmospheric physics in your laboratory by creating an ice nucleation with terahertz or Doppler cooling of water molecules. So, this is a topic that's been sort of studied for a very long time, the idea of generating temperature jumps, these T jumps in water. And this is something that, to follow on your question, has been done with a lot of infrared light. It's not a settled argument. There's a lot of, one can talk about OH bending modes and vibrational modes, but when you have multiple monomers at once, there's a lot of coupled effects, thermalization pathways, and so it's actually really complicated. I just wanted to show you there's an HOCOM paper in 2020 about how different coupling mechanisms in water still activate each other. So this is complicated physics, but if we narrow down to a really simple picture, let's just forget about coupled effects and many body interactions, and I just have my water monomer. So this is, what the question was about. People have been excited for a very long time, these asymmetric stretching, so sort of having the different OH modes vibrate at the same time. It can be at the different times or just pi shifts, so sort of breathing at the same time or just with a pi shift. It can also be this bending mode. So these show up here in V1, combinations of them show up in you look at the wavelength range at around 1.4 micron, 2 micron. And so you can activate these really highly. Librations just happen after you reach about 7 microns. This is a really flat plateau, and it goes all the way to the microwaves. That's why, again, you can heat up things with microwaves. So this is the range that we're talking about. And so there's nothing wrong with using these modes, but we want to focus on librations, particularly because these are some simulations that we have. You can see that if you shoot, for example, a 30 terahertz pulse at 100 femtoseconds, this is perfectly doable in the laboratory. this is showing you how this pulse energy here in black can transfer energy into the water vibration in both translational and rotational modes. This is for two different pulse intensities, so 10 to the 12 and 10 to the 13 watts per square centimeter, and result in an equivalent temperature jump. So this means as a matter of femtoseconds, with 10 to the 12 watts per square centimeter, I can create maybe 20 Kelvin or so temperature jump. That's not a whole lot, but that is sufficient to activate a lot of biology. And then for physical chemistry, for supercritical like water, realize that I can go from about room temperature, and again, take this, it's not real temperature, right? It's a temperature equivalent. We're still in the non-equilibrium system. It's a metric that it's easy to wrap your mind around. You can create a temperature run of about 500 Kelvin in this fast time scale. So this is how you can create this supercritical like water structure. So this is just showing you a little bit of the same plot, but just for a different example and sort of THz conditions. But ultimately, what you can have is very flat and strong absorption range in the libration range. What this allows you to do is to pick a frequency that your system, say your protein or your physical system, doesn't directly react to. So what you want to do is bypass photoreactivity of the system, and you want to activate the water, so the water activates the system. This is a bit the trick that we're trying to play. And water structure changes dramatically, and we can measure that with X-ray scattering. These are the plots, if you remember that animation where there was rings created. If I radially integrate that ring, I get these scattering peaks. This is a traditional X-ray technique. So what I can do is, as a matter of time, I can see this peak ringing and sort of breathing at this, sort of with respect to time. And this is how I can measure distances between OH, HH, and the hydrogen blood network. So I can measure this directly. So, before I delve into some of the new science, this is, after all, I think it's prospects or opportunities is what the title said. Let's just review some of the ongoing literature. There's already been some studies. All of this is thermalized. So basically exploiting these steps of motions. There's going to be some studies about how the water structure changes surrounding a physical chemical system can change its reactivity simply because I create a temperature jump. So essentially, this is nothing really new. It's just the confirmation that when you cross a temperature barrier, reactants can become more or less reactive, right? But we can visualize this, and it's been done with synchrotrons. So essentially having a laser, in this case IR, and then pro with X-rays. In biology, which is again the focus for today, there's been a lot of protein, DNA, and bilipid layer sort of measurements. Also, again, thermalized. So here I heat it up, and then I measure the result afterwards, so nanoseconds and milliseconds later. But there's already been some early studies here. There's some really interesting papers on what actually happens, right? This is why collective effects are so difficult to measure. I can talk about different monomers absorbing light, but what happens if I have a first hydration shell surrounding a protein that interacts with the electrostatic potential of a protein? You actually have a protein and a first layer of water surrounding it, and a second one. How many layers do I need to heat up? What is the density effects? Doesn't matter how I deposit the energy, doesn't matter if it's an OH resonance or vibration, the electrostatic potential will change dynamically. So this is a bit the open questions that we want to answer. And some of these things can show you that reactivity of certain proteins, for example, change depending on how close these different proteins are. Okay? So these are all unknowns. So here are the challenges ahead of us. If we want to understand water reactivity in biology or any of the systems, we need to have really high sensitivity and selectivity of these dynamics. So again, we're talking about femtosecond or better time resolution and sub-angstrom spatial resolution simultaneously. This is why we need to develop really fancy, really sophisticated instruments. You would want to do it perfectly non-invasively. In some of the examples I gave you, with destroying our samples, that presents certain challenges in the science. And then, and particularly in terms of theory, it's not enough for us to say we're exciting these water dynamics or this water absorption range. We need to understand all the collective effects. What are all these water monomers doing surrounding this particular protein, and how does dynamical interplay play out in some functional property of the protein? So this is, accessing these different challenges or tackling them is what might give us some idea on how we can understand and then ultimately control some protein function. Again, it becoming a drug, a therapy, or any sort of reactant. To give you a bit of motivation, as in this is not a moonshot sort of project, we have some early results. we did run some experiment recently where we have lysozyme. It's a model protein, and we looked at some functionality of it according to this idea of exciting water. So meaning there's a lot of protein dynamics that have been studied, but oftentimes it's a dynamical process that is non-relevant. It's meaning it doesn't have a biological relevance. In this case, what we did was take a lot of sort of snapshots. I'll show you in a second what the data was, but you have this lysozyme nanocrystallized, is this protein, and it was crystallized with an inhibitor next to it. And what we did was shoot an IR pulse at a particular bending frequency and coupling the energy into it and then probe its state at different time scales. And what we were able to see is that this is a bit advanced for people that are not used to seeing density maps, but what we can do through this crystallographic experiment in X-rays is we construct a protein map with the electron density. What we can see really well is where the electrons are, the electron cloud is. And then you try to observe charge migrating from one place to the other. So that's just what you're seeing in this density maps. Basically, what we were able to see is at 20 nanoseconds, there was not a huge difference in the density maps, meaning we hadn't really created any strong dynamic set. But at 200 microseconds, there was a strong sort of migration of charge in this particular direction in this map. And what we're able to see is that this created directly a conformational change in the protein that enabled it to bind to this particular inhibitor. So what I'm trying to say is that when we activated the water at this particular frequency, the protein at about 200 microseconds changed shape. And when it changed shape, it was able to bind to an inhibitor. This is a way that we think it could be a future way to produce sort of personalized drug delivery, meaning Aitzol here has an element, and we can sort of synthesize in the lab specific protein that is going to help particularly that element, but that protein cannot be active until we, for example, activate it with a thermal barrier, right?
Can you prove that it will not bind unless you activate the water the way you do?
This is particularly what we just did here. I'm not showing here the particular, the schematics that we have, but we were able to see is when there was no laser with a temperature jump, there was no binding. And when there was a temperature jump, when the kinetic barrier was passed and the protein changed slightly shapes, there was binding.
And for example, with other stimuli, for example, just raising a little bit the temperature, it also did not bind.
In that case, it doesn't bind as much. And this is a great question. This is why we can't just say there's this much temperature jump. It has to be, what are the pathways to get to this thermal state, right? And if you do it with this like heat, the sort of the transfer to the protein, the energy transfer is a very different mechanism, right? The mechanism with this is activating some vibrational mode of water and something between the first hydrogen shells surrounding the protein make that protein activate.
And before the temperature jump, what is the temperature of the solution?
It's about room temperature in this case.
Room temperature.
So this is a bit the idea. I hope that the gist of the idea is coming to terms, right? We can't just say this is a thermal process, you get to this temperature, you activate the reactant. Sometimes it does happen. But playing with the molecular dynamics surrounding this protein can affect dramatically the end result and the functional properties of, in this particular case, lysozyme. So anyway, this in press, it's being reviewed in Science right now, but you can read the article better in the bioarchive. This will be recorded, so you can check it anytime. But that was a bit the motivation. I want to talk more about challenges. This is, what are the ingredients to make a real leap in this particular field? Because as I mentioned, at most we can take a few snapshots in time. In this case, it was 3, and we need to build a puzzle with that, and it can be quite difficult. So one, and I'll be touching on all these topics briefly, is the development of more instrumentation, particularly compact electron sources and X-ray sources. I'll show you in a minute, if you haven't seen it, how big synchrotrons and X-rays are, not just big, but how expensive. And also tunable high average power, both mid-IR, far infrared, and terahertz sources. These are the ones that cover these OH resonances and their librations as well. This is something that Teresa started working on when she spent some time with us at SLAC. The sample delivery methods, that I would say is part of instrumentation, but I would even categorize it separately. It's really difficult to build microfluidic devices to deliver these proteins to an exfil. Much more so with electrons. Electrons require really high vacuum. Photons don't really care. They might get absorbed, but electrons will not propagate. And so having liquid and vacuum, it's mutually incompatible. And then having photonic integrated circuits with, how can I couple THz in something that looks like a photonic integrated circuit with some microfluidic device, that could really speed up how we run these experiments and eventually deliver functional biology. In terms of fundamentals, this is really questions for the theorists. And we begin to understand this pathway from room temperature, for example, idle state to a thermalized state. What are the manifolds in this non-thermal, non-equilibrium sort of pathway, depending on how we excite the water? And then can we explain reliably collective effects? And last but not least, you might have seen this with AlphaFold and recent things coming up. When you ask the biologists, there's at least 200,000, if not 250,000 proteins statically today in a database. So this is well understood, the structure of proteins. This is how one of the main reasons why the spike protein for COVID-19 vaccines was delivered so quickly is because we had the structure. But we don't have a dynamical library yet. And many people would argue that an idle state protein, a static protein, doesn't give you as much information as its dynamical properties. How does it move under different conditions? So this is something that the community is sort of galvanizing to produce. So let's just touch on some of these topics. I just want to give you a bit of a sprinkle, and then we can talk more about it. So probes, again, we orchestrate some motion, we shoot a laser to water, but how can we probe that? Talked about that for a little bit. I haven't really mentioned the electrons much. You can sort of excite a system with this laser and then probe with electrons the same way that I can do with X-rays. Nice thing about electrons is that I don't need them to be very relativistic. They don't need to go too fast. For them, they have really high scattering cross-section with matter. This is why they get absorbed really quickly. So you can get essentially scattering from the same way that you can get those water rings. You can get the same thing with electrons. There is a handful of these sources in the world, a number of them in Europe and Asia and North America. I'm just showing you an example of how this looks. Just about 5 meters. It needs to be radiation shielded because electrons are, cancer in this particular case. It produces a lot of radiation. It is a decent facility that has already shown to have a lot of relevant results, particularly in chemistry and material sciences. These are some numbers. I'm not sure that they make a whole lot of sense, but they basically speak to how tight I can focus the electrons, and this is a really important metric. Since we've been talking about ultrafast, the one thing that I can mention is that the temporal limit currently with ultrafast electron diffraction is in the order of 150 femtoseconds or so. So this is the fastest I can do. And I was talking earlier about being able to do sub-femtosecond. So we're not too far-fetched, but there's some room for development here. Now, XFEOs are the real sort of revolutionary source here. XFEOs, if you look at them in a schematic, they look really simple. All you need is an electron bunch like the one that I showed earlier, but instead of going at 4 mega electron volts, this is about 70%, 80% of the speed of light. They have to go at 99.999 the speed of light. So this is about 4 GeV. While I need 5 meters, accelerating electrons to a substantial amount of the speed of light is relatively easy, but once they're relativistic, getting them an extra kick is really hard. So these facilities are 1 kilometer, 2 kilometers long, and it's just one single laser, so one single user, right? But what you do is, simply speaking, throw an electron beam that goes really fast to an undulator, and as it starts undulating in this magnet, sort of isolated magnet, every turn it loses some angular momentum, and if you do it right, that angular momentum needs to go somewhere, and it goes in the form of a photon. And the electron beam might begin to bunch itself, and you begin to have actual lasing, meaning the electrons are cloned and coherently amplified. And that's when you start having this microbunching is when you have this coherent addition. So that's why it's a laser, but it's not the traditional cavity. This is the typical diagram. When you want to go to, you can in principle do this for the visible, for the terahertz, for the X-rays. There's terahertz FEOs out there, but they're really expensive. So why build them when you can do them cheaper? They're really useful for the hot X-ray range, for 1 keV, 10 keV, because other than synchrotrons, no other sources can really deliver hard X-ray pulses here. And we need the hard X-rays to be able to get really high spatial resolution. So these are some of the facilities here in the LCLS, the European XFEO. Is a bit outdated, but it gives you an idea of how many orders of magnitude more billions you can get. So you can get, single shot images. This is why you can afford to destroy your sample, because you acquire an image in a single shot. I wanted to show you really briefly, essentially, just how, we won't have much time to go into this, I'll be happy to discuss it, but how we can shape exo facilities. This is a schematic, a miniature schematic of how they work. Essentially generate an electron beam. This can be done with a laser. You can condition the electron beam on an undulator. This is not the one that lasers. You can shape it, in this particular case with a donut beam. And then this is the part that is about 1 kilometer, if not 2 kilometers long. It's really, really long and has many segments. And in this particular case, you have the first undulator. This is SASI. If you're, savvy with laser optics, SASI self-amplified spontaneous emission. So it's kind of, you begin to have SASI mode, meaning something that lasers from noise. And you can take a chunk of that to seed a second part, and now you can seed your laser. So it can be really monochromatic. And this is a trick that we've been playing recently, using these donut beams to shape it to be able to create really monochromatic X-ray pulses. Something that happens with X-rays, and this is a bit of a challenge today. If you look in here, is that because the process is born out of an electron beam, and one of the electrons has to first emit one photon, and that comes out of noise. Your longitudinal coherence, it's a laser, it's spatially coherent, but your longitudinal coherence is non-existent. So you have all of these spikes that essentially in spectrum are different parts of the electron beam lasing at different times. So you don't have longitudinal coherence. That means in spectrum, you don't have a whole lot of monochromaticity, and it's really jittery. And so some spectroscopic measurements require a really particular color to be excited. And you can do that with seeding with this new scheme that we demonstrated recently. But this gives you, I mostly want to show you the idea of how complex these systems can be. You need about 20 people per hour running any experiment. It's just extremely expensive and complicated. And this is how it looks. You have, this is just the laser itself, right? And this is 2 kilometers. And they have multiple hatches sort of running different parts of the experiments. I just want to show you a little bit how this works. I'm, again, happy to answer any questions in that regard. In terms of X-rays, maybe the most noteworthy recent development that was demonstrated just 2 years ago and now can be somewhat routinely operated is that we can bunch the electron beams. We can sort of compress them to something that looks like a pancake to be able to emit at-a-second X-rays. This is completely revolutionary. X-rays used to be in the femtosecond range, 10, 20 femtoseconds at best, similar to electron beams. But now we can drive some instability to be able to laser at 500, 300 attosecond. So now you have a powerful X-ray beam with, we're beginning to get to those magic ingredients that I was talking about. This is somewhat routinely done, but it requires a lot of babysitting. So it's not really straightforward. It might need another 10 years until it becomes routine. Okay, pumps. So I talked about X-rays and electrons for probes. Pumps, tunable, UV visible, and EIR lasers are really common in most ultrafast time-resolved experiments. Mid-IR, far-infrared, and terahertz sources are also becoming more frequent, but they're not as well established, right? And so I just want to give you a bit of an overview of what the state-of-the-art technology is. When it comes down to using lasers to generate far-infrared or terahertz, there's multiple ways to do this in nonlinear optics. It can be through optical rectification and organic and inorganic crystals, or through difference frequency generation. So through DFG, you can get particular bands, for example. Through optical rectification, you can get very low range, sort of sub-terahertz range, very narrow sort of ranges here in the frequency domain. And then sometimes you can generate plasma in error. In reality, if you pump anything hard enough with a laser, it will generate some X-rays, some terahertz. But the efficiency is really, really low. So you really want to create a temperature jump, or put a lot of energy into water to create supercritical-like water structure. You need some energy, right? It's feasible, but not that easy to produce. So 2 examples that I wanted to bring up are P-plans and lithium niobate. This is relatively straightforward. If you shoot a laser into something that looks like a quasi-phase matched nonlinear optical crystal, it will get rectified and produce as many cycles in the terahertz, basically as periods you have. So there's an easy way to generate something that is relatively narrow. And pay attention here to the SAP 1 terahertz range. So I can have this at different cooling temperatures and tune it and have relatively high efficiencies. This is really well established. Another way of doing this is through optical rectification. It's very similar. I shoot one IR pulse into something that looks like a prism. In this case, it's a total pulse front. The main difference with this approach is that this is when I want to produce a really broadband terahertz pulse. So what you can see is in frequency, it occupies this entire span here. So it would be really broadband. And instead of being multiple cycles, it's just a single cycle. So these different sort of cycles give you a little bit of a tunability in driving the process and orchestrating it. This is, I work quite a bit on this issue. This is not too difficult. I think one of the main issues is to not only produce these pulses, but put them together again with a liquid jet and a vacuum chamber next to a big, large-scale facility, right? So there's a lot of developments underway. These are, for the laser jocks in the room, if anybody wants to see what's happening lately is some of the developments that we have at really high repetition rates to produce high energy terahertz pulses. Nothing scientifically compelling here, just lots of engineering. One alternative way, just to give you an idea to produce terahertz, is to actually use electron beam. So if you remember, I can wiggle the electron beam and produce X-rays. If I use magnets that are really long and the electron beam, instead of wiggling really fast, wiggles really slow, I can produce terahertz with the X-rays, terahertz with the electron beam, and I can couple that into an experiment. So there's recent developments in all of these large-scale facilities to take a little chunk of electron beam and pass it through a different angulator to produce terahertz. So I can have terahertz next to my X-rays or my electron beam. And I want to touch on, that's for pumps. I want to touch a little bit on some of the techniques that we have available. I talked briefly about this. So this is what we call time-resolved X-ray scattering. So say I have my molecular system, an idle state. Say I pump it, right? I say start the motion, deposit energy, and sometime later I come with my X-ray pulse. And at that point, I can take some scattering, diffraction data, whatever it is. I usually work in the Fourier plane. So these are the same plots that I showed you earlier. When I have water, because it's disorderly, I create a water ring. Basically, every sort of electron cloud is going to scatter because I don't have control over the orientation of the water. It sort of diffracts in the same angle, and all I can do is sort of angularly integrate and get this. So basically, this one particular peak would be, for example, a ring in this way, and then you can see the ring breathing. But when I, for example, put my terahertz range there, because the water aligns with the polarization, the electric field, I can see an asymmetry in the ring. So the ring might shrink down in one direction or the other. So these are some of the ways that you can tell the water structure changing. And so, this is what you can reconstruct from these experiments. You can basically look at the RDF is the radial distribution function, just a little jargon, but this is basically as a function of time from minus times, meaning the water is not pumped with terahertz, and then it's pumped up the way all the way to 1 picosecond. What are the distances in angstroms between two oxygen atoms and two oxygen hydrogen atoms? So you see the first two oxygen atoms, and of course there can be another oxygen atom from another water monomer. So you see those peaks breathing in intensity. Yeah, this is a typical technique that you have to observe this molecular motion. Right now we're running an experiment where we're trying to see this in physical chemistry. So can we see the ring of phenol sort of breathing as well? Not because we activate phenol, but because we activate the water around. So this is just a little playful experiment that we're trying to run. Yep. And this is another technique outside of X-ray scattering. You can also excite water at a really low X-ray energy, with XUV, for example, and generate electrons. And now you can detect the electrons. So this is time of flight electron spectroscopy. And this is some of the data that we were able to see recently. You've seen here the binding energy of the electrons in the first few molecular levels of water. And in this particular data, you don't see it very well breathing, but you can obtain some data about the redistribution of these electrons as a function of time. So let me show you some recent and still being, this is data that's still being analyzed at the moment. What we were able to do is a flash, this is in Hamburg, is the only FEL currently in the world that has had that trick that I talked to you about, having an XFEO that produces both terahertz with electron beam and XUV. And so what we have is this really complicated experiment where we throw in the FEL, and here's where the liquid jet was installed, and the terahertz is essentially coupled in there. And we have a time-resolved experiment where we can generate electrons, and then the terahertz field can streak the electrons. And so we can see for the time being some gas phase, some liquid phase electrons. So these are electron energy streaked by the terahertz field. This is essentially a terahertz field. And we're beginning to, this is our data. You can see there's no even access quite yet. We just sort of reconstructed this a couple of days ago. But this is literature from early on in sort of measuring different phase states of water. And we can begin to see some secondary electrons coming out. These have to do with intercolumnar decay of water. There's a whole different sort of field of study within biology that I also can touch on in the Q&A anytime you want. Just to give you an idea, photoelectron spectroscopy is an alternative or complementary technique as well. And I'm coming sort of to the end of some of the topics that I wanted to cover is, I talked a little bit about how we can pump the systems, some of the biology as a motivation, some of the early results we have, techniques in these large scale facilities. But again, I can try to motivate all of these science cases as much as I want to, but I ultimately have to go to these facilities, wait a couple of years until I get beam time. I get a couple of days. If I'm lucky, I get some data. This is not an effective way to run science, right? So access is an issue. And so this is a lot of what we do in the group. I just wanted to probe two questions that I don't have answers for. So this is just good to think about. I also have to say this because my PhD was on building compact X-ray sources. Everybody's been promising compact X-ray sources for decades now. And it's just become this, I don't want to be part of that team, but I still work on that, right? So we need to have an honest conversation as to how we can materialize compact sources and what they can do and they cannot do. But could we use new sort of emerging theories in quantum electrodynamics to produce or materialize compact sources that can do some of this science, maybe not all of it? I will actually talk about this. Second one, I don't, and I want to pick the theoreticians' brains here. If I'm able actually through some of this new theory, have not only X-rays or electrons, but can use both of them at the same time, have some multimodal way to couple electrons and X-rays at the same time, can I have new insights into couple effects? So for example, excitation manifolds that are uniquely driven by either photons or electrons. Can I enable new science, not just have compact sources, but new capabilities? This is just food for thought. But to tackle the first question on access, I'm part of this consortium. You might have heard about it, maybe not. It's called A-chip. It's accelerator on a chip, and it's one of the good examples noteworthy. These are essentially dielectric accelerators that rely on a similar technology as the RF accelerators, the long accelerators that I showed you, but instead of being driven by RF fields, by optical fields. So what I have is something that looks this small, and I can couple in light. It would have accelerating gradients. If I put an electron beam through this channel, it might get accelerated. So for comparison, the state of the art on this technology is being able to produce 60 to 150 keV electrons. This is still 30–40% the speed of light. Getting it to the MEV level, which is what you need to do UED, ultrafast electron diffraction, is quite challenging, but they're on the way. This is one of the metrics that are really useful to mention. Earlier, you might not remember, but I was showing you 10, 20 micron spot sizes. I can now focus this to the nanometer range. I could eventually focus into single isolated quantum systems, which can be really powerful. But the most important aspect to these bunches is that I can produce the macro bunch because it gets, basically when I insert an electron beam into this channel and it gets accelerated by electric field, it gets bunch in the buckets of the electric field of the laser cycle. So if I use 1 micron laser, for example, it naturally will bunch in every cycle. So the electrons will fall under every bucket in the cycle. As you get naturally this micro bunching, that can be pretty useful because I can isolate one specific bunch and they are naturally already 270 attoseconds. I don't need to do anything about it. It's just by nature of the field itself. It just needs to fall inside of the field and they get compressed automatically. So you get 270 attosecond electron beam here. What is the caveat? That I can't really accelerate many electrons per shot. I get, on average, even less than 1 electron or 10 electrons per shot. And I need about 1,000 times more to get a good UVD signal. So anyway, this is one ongoing development, really interesting following up, but it has some serious trade-offs. This is a bit the new emerging theory that some collaborators have come about that we're working on, and we've been discussing with, most recently in some conferences. The idea of exploring good old Bremsstrahlung radiation. So Bremsstrahlung radiation, just quick overview, is what makes X-ray tubes work. You go to the hospital and get a chest X-ray. This is the machine. You take an electron beam, you accelerate it. Don't worry about shape, quantum electrodynamics, or anything. If it hits a solid target, usually tungsten or a piece of metal, it just emits X-rays everywhere. They're really broadband. So they tend to have this sort of conical shape. This is what you're showing you here is this in keV and photon energy. So if you have 20 keV electrons and do that, this is the atom here is symbolizing the barrier, so sort of a metallic target. You essentially have something that looks like a conical radiation and it's really broadband, right? I can't really control it. 200 keV, same thing. It's just more energetic photons and a little bit more reduced, but still conical emission. Under normal QED theories, I can think about having 2 electron states, but they're still remaining coherent, meaning you can have two different electron wave packets, and they both will emit radiation. At the low energy range, there tends to be practically no difference. When they become more relativistic, you can see some additive effects. There's no actual interference between them. What we just recently found out, particularly through a theory from some colleagues in Singapore, is that if you actually can control a coherent multi-state electron, and this is possible, meaning you create two different states of electron beam. It can be momentum space, or electron beam crossing at an angle with a prism, for example, or two different energies, meaning you look at the spectrum and there's a binomial distribution. Their contributions, the branch-only contributions, can actually interfere, just like any other field interference. And in the case of two states, you can take this conical emission and reduce it to having a directional on-axis emission. This would be 0 radian, would mean the light goes in the forward direction. So there's already an improvement. But you can see that I still have a little more monochromaticity, but still relatively broadband. Similar process at 200 kV. So this is just a bit of an introduction. We can ask ourselves, okay, that is what happens with two coherent states. Can I continue to suppress or enhance certain parts of this emission by adding more states? The answer is hopefully yes. In theory, yes. We're working on this experimentally. Imagine that now I have multiple electron states, so not just two of them, and I'm going to say they're in momentous state, so they're coming at an angle, and they're going to come and interfere, for example, with a graphene flow. But this is again an atomic barrier. And as a result, the electrons will scatter, and I will have some photon scattering as well. Here, NS and NA designate the eigenstates of the electron bunch. So N1 means it's no shaping, it's just one electron bunch. And the NA is how many atoms in the graphene it interacts with. So here, we're just normalizing the plot to show a little bit what I'll show in a moment and more visually, but you can see this exact same emission as this conical broadband emission. Let's see what happens if we add 6 electron states interacting with a single graphene atom. You can see that my intensity is not really high, but I'm beginning to have a very, very directional and a little more monochromatic electron beam moving forward. This is because while you have a lot of electron states, if you don't have more interaction with other atoms, you're not going to have this collective effects really give you a lot of enhancement. Now, let's say if we added 2 graphene atoms in this particular case, I can have, with a specific 6-state configuration, I can have a substantial increase in the brightness of this field. Again, focused on the on-axis emission and in a relatively, more narrow band sort of emission. And instead of 10 to 20 kV, most of the emission happens within 2 kV. And I continue doing that with more states and more graphene atoms. And I can wind up having a really bright sort of source, for example, that is much more monochromatic than the ones that have been shown before, with the brilliant sort of scales with number of atoms. So this could give you a scalable way to continue adding multiple graphene layers and coherently adding to create a more monochromatic X-ray pulse if you need that, and more directional. Creating 20 kV electrons is a walk in the park. I can do that in just 2 centimeters for $10,000, as opposed to multi-billion dollars that these other facilities cost. So this is both in the energy domain and in the directionality domain, but I've been talking about ultrafast. So we won't have time to talk about this today, but of course we have ideas to take this electron beam and longitudinally compress it. And at this point, you would have this type of emission, but also in time domain would be a really short pulse. And this is sort of, these are definitely crazy ideas. I'm not really sure that they'll ever work, but we are considering them very seriously, which is the idea of mode locking and exafield. Mode locking optical lasers has been around for a few decades now. It's been revolutionary, but for that, traditional mode locking in optics means you have to have dispersion management in a cavity, controlling both linear and nonlinear properties. There's no cavity in an X-ray, it's just a linear process. So the question is, what does it mean here, right? So this is another theory paper that's been around for about 80 years now. No actual experimental deployment, but in theory, if you can control an electron wave packet longitudinally to have a specific energy modulation, you can make it go through an undulator and control dispersion linearly and non-linearly the same way you would do it in an optical cavity, so that what you wind up having is, in the frequency domain, sort of an angstrom spacing frequency column. So this would yield, again, naturally out of second duration X-ray wave packets that are very, very stable in the frequency domain. So you can run the same way that you can do uniquely stable frequency domain spectroscopies with mud-like lasers in the optical range. You could do this in the X-ray. So that means probing inner core electron motions, for example, with very, very precise sort of selectivity. So these are ideas that we are currently working on as well, both in theory and experimentally, to try to develop some of these sources with longitudinal shaping such that we can also exploit them to have ultra-fast duration. These are just some ideas on how you can exploit sort of plasmonic effects. There's lots of ideas out there. So again, many trade-offs. I'm happy to sort of present a little bit the pros and the cons of what they are in discussion. But I think this is good enough to sort of recap a little bit what I talked about today. Hopefully, you believe the idea that non-equilibrium physics are everywhere. They're really elusive, oftentimes ultra-fast, oftentimes quantum, but not just that, can have something to do with thermalization pathways, loss of coherence, a loss of memory. And this is a field of study that is very much untapped. One of the reasons is because we don't have good instrumentation to probe it. When it comes down to studying this non-equilibrium dynamics, you need these atomic timescales and spatial resolution to be able to analyze and see what is happening in both space and time. When we focus on non-equilibrium dynamics in biology and chemistry, I hope that I could motivate that water is not just a universal medium, but it can be a very, very broadly applicable medium beyond photoexcitation of proteins, for example, or physical systems, to activate the water and use water as a medium to create further reactivity. I give you a quick example of lysozyme, linked to this inhibitor binding, and look for that publication soon. In the near future, we're going to be looking at the same function of lysozyme, but under different coupling conditions. So basically, does the protein binding change if I do it with OH stretching or OH bending or libration? What is a catalytic reaction? Can I control this catalytic reaction? And then instead of instrumentation, I give you a bit of an overview of what kinds of probes we can use, what kinds of drives we have and methods. They all are really complex and have multiple trade-offs. So by no means I'm siding with one camp or the other. But I think what's common for everybody is that accessibility is an issue. I'm really excited about this new QED theory and recent experimental developments to work on this. And hopefully one day, maybe my lifetime, will have truly ultra compact, inexpensive on-a-chip UED and X-ray sources. So just a quick acknowledgement, it takes a village. So it's not just me, it's a huge number of people working together, both in my team and our collaborators. These are some of the core people that are instrumental in the science that I showed. We're co-located at UCLA. And of course, this is an aerial image of LCLS. This is exactly 2 miles. Funding from the sponsors. And then we have a couple of open positions. And research associate, this is a postdoc level position at LCLS. So this will be based in the Bay Area. So please send me an email or just advertise this opportunity if you hear from anybody. And thank you very much for your attention.
Thank you very much, Sergio. Eskerrik asko. We have, 10 minutes for questions or something. I don't know. Does anybody in the audience want to ask something?
I have a question.
I could see your face, but not yours.
In the slide, I think it was 17. It was only water.
Maybe here?
Yes. There you have watershed. It's only the experiment. It's only bulk water. No.
Yeah, and so there's two. Yeah, and this. Yeah, forget about this drawing down here. In this particular experiment, what you have is just a water jet. Maybe some properties of the water jet I'm mentioning is that in this case, it's about 20 micron or so jet. It comes in at room temperature, but the moment that it goes into vacuum, starts icing. So it's not really clear, but at some point, if I were to look at it down here, for example, by now it's ice just because of the lack of pressure. So just water starts expanding, goes into this phase state. So we try to probe it as soon as it comes out of the nozzle. What you expect to see is just liquid water, roomish temperature, and disorder. So it's just going all over the place. That's why you get somewhat of a ring. And then the idea is you can use the same experiment now, can introduce, crystals, for example, for proteins, the crystallography. They can be phenol, which is the example that I'm showing you here, so I can add some physical chemistry system there. Early on in the motivation, I showed some formaldehyde, for example, so I can do waste reduction. If we haven't done that yet, but if this was a hazardous waste, I could try to create supercritical-like water structure and probe it at 2 different timescales and see how, before it's pumped, I just have one chemical system. And after it's pumped, after a certain time, maybe that physical system has broken apart into 2 different compounds. Maybe I can see that reactivity. We can't see it quite yet. Again, because I'm talking about molecular films, but in reality, so far the accessibility and the complexity of this experiment is so high that we get a few snapshots here.
But in some way, the technique is local. I mean, you are measuring local. This is something I don't understand exactly, because when you have a protein with the water, you have a lot of water molecules with the proteins. But you are looking with your technique, with the laser, you are looking at particular in some way local.
That's right.
It's in this way.
Yeah, so you're completely right. I'm trying to paint a simplistic picture, but you do have a very localized, I mean, even when we talk about temperature, where do we say particularly the temperature has been deposited, right? But what you expect in every one of these events, for example, every time I pump a system and probe it, is to have a relatively confined sort of 10 micron-ish sort of cross-sectional area that I orchestrate and then I probe. So oftentimes while it is locally probed, you see a lot of collective events. I can't just, my water ring, for example, I can't isolate which water ring, which water monomers will participate and which not. Yeah, there's many statistical tricks that you can play to say that with a lot of certainty, but you technically are probing collective effects always. So I need to know something about my system, right? This is why, in this particular case, water is really easy to model. So I can say these particular peaks that correspond to OO and OH distances. But imagine if I have an organic compound and there's all kinds of, that needs to be really well calibrated. So it can get difficult very quickly. And that's why there needs to be a lot of computational biologists participating in these particular experiments to understand what we exactly looking at.
Okay.
Okay, thanks.
I have a couple of questions, but probably there will be so stupid that please.
How unique is water in this activation processes in biology? For example, if you do the experiment with different solvent and you shine with the laser on the solvent, trying to initiate this similar activation, would you see the same triggering of the biological process or not?
Yeah, that's a fantastic question. So first order, I can say we can't say experimentally yet what the exact difference is. And the role of water in this particular system and in producing, I want to make the distinction, functional biology is believed to be very relevant compared to any other solvent. But in reality, if I forget about functional biology, if I just care about structural biology and changes, if I put a protein in any solvent and I excite the solvent or the protein, I will surely see some reactivity. It could be in a conformational way, meaning the shape of the protein has changed. It could be in a charge transfer mechanism. It could be in some isomerization of the protein. So there's lots of experiments since X-fields have been around, about a decade now. There's a lot of experiments in biology that show you some change of the biological system. But I have a feeling, and many people in the field have a feeling, that that's been somewhat of a playground to test all the instrumentation methodologies, computational statistical analysis. The question really is, okay, we can see some change in a protein, but is it of natural or biological relevance? I can put it in some solvent, but in what case scenarios is that protein going to be embedded in that solvent and control under this particular case scenario? So water is a reliable medium where a protein might be embedded or some sort of water solution. So this is why to study functional biology, water is not the only medium that is the primary suspect to control any reactivity that is biologically relevant. That makes sense.
Okay, well, if you don't go that far to a different solvent, if you take deuterated water and you do the same experiment, thermodynamically, the for example, in your case, the binding of the lysozyme would not change, but the dynamics probably will of the binding.
Yeah, that's a great question. We do not know. that.
Okay,
We definitely do not know experimentally. It could be an interesting problem to work on computationally. But again, there's computationally and experimentally, there's still not a whole lot of agreement between what we can observe in the laboratory and what theorists can model. So there's still a bridge to sort of a gap to bridge in there.
No, but the deal, you can repeat this experiment with.
Yeah,
just-
absolutely.
Yeah.
Yeah, absolutely.
Okay, I just checked and it's past 1, and I can save my own questions for later because we're having lunch now. So if there is any last minute question, this is your time. If not, please, let's thank Sergio. And pretty much it. Enjoy your week. Bien. Estoy sorprendido porque he pensado fatal sobre este seminario. He pensado en toda la gente de óptica, pero se me ha olvidado totalmente.
Sí, yo cuando vi...
Claro, pero soy lo suficientemente rápido para daros cuenta de lo que os interesa.
Exacto.
Pero le mando segundos emails a
Gracias.
Aitzol a los pacientes en plan, oye, vení, que esto os puede interesar, no sé qué.
También me parece que sí, ¿no?
Pero no me he dado cuenta que a vosotros os interesa.
Mucho más, porque si puedes cambiar, obviamente. Gracias.
¿Qué dices, no?
No, que a otro grupo en óptica, toda esta parte de las que es.
Yo pensaba que iban a venir con más los de óptica y todo esto.
Bueno, a mí me interesaba la parte de los tercios, ¿no? Ahora estoy trabajando en esa parte, pero sí, muy interesante la verdad.
Pero Sergio, mi pregunta principal era, ¿por qué no se puede hacer con Raman esto, que es más barato?
También se puede hacer.
¿Ah, también se puede hacer?
Se puede.
Vale. Pues no lo pregunto porque he dicho, voy a quedar como tonto
No,
total.
de hecho, no sé, bueno, me he enfocado en un par de técnicas. Raman, X-ray Raman, Spectroscopy también es
O sea, puedes hacer el PAM con Raman y el PRO con X-ray.
Al final depende un poco, yo creo que entre todas las técnicas acabas teniendo un poco. Mira, el X-ray scanning es muy fácil de hacer, pero es lo que decía, si tienes un sistema bien simple, con un par de elementos, pues es más fácil de interpretar los datos, pero una vez tienes más átomos o si te vas muy lejos, vete a ver qué sacas de esta.
O sea, yo lo que me quedó por preguntar es.
Ha trabajado conmigo en el pasado.
Sí, bueno, seguimos casi.
Sí, bueno, tenemos un paper por ahí que no
Está ahí,
pero bueno.
¿Cómo separáis estas vibraciones colectivas del agua? ¿Son las que activan la reacción de la proteína o no es la propia proteína que tiene modos colectivos, las rotaciones, ¿no? Porque estamos en ese límite.
Sí, es un poco difícil de averiguar. En principio, hay información estática espectroscópica de dónde están las resonancias de la proteína. Yo no puedo decir, bueno, yo voy a ocupar una que no.
Vale.
Pero es tan simple como eso. En realidad no sabemos si hay algún tipo de forma indirecta en la que tú activas un. Es que es muy complejo, ¿no? Yo puedo decir, por eso yo puedo decir, bueno, yo activo el agua, algo ocurre con la proteína, pero a medida que está cambiando en algún punto intermedio, mi espectro va a cambiar. O sea, su espectro, por ejemplo, la absorción. Entonces, de repente puede haber una transferencia. Por eso, la idea de lo que estaba intentando dar un poco la idea es que siempre hablamos de temperature jump, los biólogos hablan de temperature jump, pero dices, es que puede haber un montón de formas. Por eso, la sospecha es, y los experimentos somos emperadores, que cómo produces ese temperature jump, o sea, te dice todo sobre cómo va a acabar siendo el sistema.
Sí.
Entonces, pero no sabemos.
Y, por ejemplo, para comprobar esto, yo no, o sea, experimentalmente no sé si es muy difícil hacer este experimento, por ejemplo, en fase gaseosa o en vacío, para descartar, digamos, el papel del agua o que viene